This is the way we used to do what I'm about to show you. I think it's outdated.
Just go into slides.
Is this one? That's probably fine.
Program?
Nah, one picture. One picture.
I got it.
There we go. So this is the way, again, you can't see it. This is the way these areas used to be computed. Now, if you look at, this is called a standard normal table. Your textbook, I'm sure, has one of these buried in the back of it somewhere. What you do is, you look up your z-score that you're interested in on this table, and then you move to the right, and it gives you the area that's underneath that particular z-score. So if your z-score was 0, which is not shown on this chart, I wish it was, but it's not. 0, if you scrolled over, would show an area of exactly 0.5. Because 0 down to this tail would shade exactly 1/2 of the curve. If you start moving to the right of that, to the right of 0, like it appears to be up here, how's your area going to compare? More or less than 0.5? More. It's going to get increased. It's going to get increased by that. So if you go out to, I can't even read, these are all negative. It's not even showing you positive.
0.3 at the bottom.
You see 0.3 at the bottom? I wonder if this has got,
Actually, I think
that's negative 0.3, isn't it? Yeah, I can't even read. Don't worry about it. This is the way it used to be done. But it's a bit of a pain because it's not dynamic enough in my opinion. So what I've done is, I've written STANormal for you. And let's show you how it works. This seems to work a lot better. So grab STANormal. Zoom in a little better. Everybody find it? Good. Fire it up. Programs, STANormal. Okay. The first thing it asks you is forward or backward. I want to make sure we understand what that is. These are terms I've made up. They don't exist, but I needed to have these terms for discussion in class. I shouldn't say they don't exist. They do exist. It's just that people call them different. They call them inverses and non-inverses. That's 2 Math 111. I didn't want to bring back bad memories. So a forward, the way I've defined these two things, you don't see it?
Gotta hit enter.
No, I have to share it with her after class. So a forward is, see if you can follow this one. A forward is you have a z or z-scores and you want an area or a percentage. We just did a whole buttload of forward problems. Now we've been doing them also all term. For example, what percent of the curve is between -2 and 2? And you guys told me the answer. It was 95%. That was what I would call a forward problem because you had the -2 and the 2 and you wanted the area. What percent of the curve is between -1 and 1? You've got the z's, you need the area. That's a forward problem. What percent of the curve is below 0? Half, 50% of the curve. It's still forwards because you knew 0 was a z-score. What did Veronica go and do? She asked me a backwards problem. She asked me a backwards problem. That's when you have the area or the percentage, right? And you want the z-score. Because your question was so good. Where's Q2? And then my question was, where's Q1? Where's Q1 implies you know a percentage. It implies you know 25%. It doesn't tell you where it is on the curve, though. That's what makes it a backwards problem. You know the percentage is 25%. You need to know at what location 25% is located. Linda!
Can we lift that up so we can...
Oh, I'm sorry. Yes, of course. So a forwards problem is when you have the z and you want the probability or percentage. A backwards problem is exactly the opposite. You've got the percentage and you want the z-score that cuts it off. Now, both of these can be done mathematically. This one can be done with calculus. This one can be done not with calculus by something called numerical approximations. None of it should be worrying you guys at all because I wrote you a program that encapsulates all of it in one little package here. So what I want to do is I want to go back and re-look at the questions we've already answered and show you how STANormal works because it works beautifully, it works gorgeously. Okay? Let me erase the board. Is everybody sort of okay with those definitions? I think it'll make more sense when we actually run some numbers and answer some questions. Let's do a forwards problem. Let's answer the questions we've already answered. The first thing it asks, do you want area between some z-scores? Do you want area left of a z-score or right of a z-score? Your guys pick. Left of a z-score. Boom. Now we've already done one of these. We wanted to know the area that was left of 0. Remember that? Remember that question we asked? What area is the left half of the curve? Well, what's the right bound on the left half of the curve?
0.
0 itself. Type in 0, press enter. It will graph you the bell curve, shade you the area you want, and then tell you the area down there in the bottom. 50%, 0.5. Half the curve is left of 0. While you're at it, press enter again. Hit enter for more probabilities. Another forwards one. Let's do a right area this time. I won't do the exact same question Jolene just told me to do. She wanted to do left of 0. We're going to do right of 0. So left bound is now 0, off to infinity. Let it do it for you. It's going to draw the curve, shade the half. You know what the answer was already though, didn't you? You knew what the answer was. The answer was going to be 0.5, because if half the curve is left of 0, half the curve has to be right of 0. It's symmetric. Symmetric. Making sense? Ish. Run a few more of those lefts and rights. Let's do another left. Forward, left. What should we go left of?
2.
Pick 2. Left of 2. This was a question we asked earlier. If you have an IQ of 130, what percentage of the population are you larger than, as far as IQ goes?
Oh.
Well, that's 2 standard deviations above, right? So if you put in 2, it's going to shade.
Maybe.
Stop at 2 and keep going. Look at that. Now, what did we say it was? Didn't we say it was 97 and a half?
Yeah.
That's because 2 standard deviations is not exactly 95%. Watch this. More probabilities. 2 standard deviations. We've been using 95%. It's not exactly 95%. Do a between this time. Do a between. And go from -2, left bound of -2, to a right bound of +2. It'll show you 2 standard deviations. But when you do it, notice the area is not exactly 95, it's a little bit more. It's 95 and about a half. Why do we use 95? Because it's easier. Because it's easier. We do this all the time. You ever heard of something called the rule of 72 in finance? Figure out how long it takes to double your money in an account? You ever heard this before? It's actually pretty useful. Take the number 72, divide whatever interest rate you're getting into it. The result is the amount of years it will take to double your money, whatever money you put in. So if you're getting 6% interest on an investment and you can guarantee 6% for a long period of time, 72 divided by 6 is 12. Take you 12 years to double your money. Whether it's $1 becoming 2 or 10 becoming 20 or $1 million becoming 2 million, it will take 12 years to double. If you're getting 2% interest, it'll take you 36 years to double your money. 72 divided by 2 is 36. Why is it called the rule of 72? The number you should be using is 69, not 72. So why do we use 72?
Divides into years better.
Because it divides into way more numbers than 69 does. Same reason we use 95 here. It's easier. It's not perfect to use 95. I believe, if I remember correctly, let's see how much I can remember. Do another forward between. Try -1.96 to +1.96. I think this is the one that's closer to 95. I think. Let's see how my memory is. It looks the same as the graph though, doesn't it? Yep, there it is. Those are actually, so technically speaking, if you want to go 95%, you have to go 1.96 standard deviation. Call it 2. Everybody else does. Call it 2. Yeah? Call it 2. How about 1 standard deviation? Forwards, between, -1 and 1. This number hopefully looks familiar to you. About 2/3, yeah? 68% is usually very often used, about 2/3. Big chunk of the curve is right there, right? So if 68% is here, what's right there? What's right here in this unshaded part of the tail?
17%.
That's that 17 we did, didn't we, earlier, right? 17, 17, roughly 2/3. See what's going on? Now suppose you don't feel like doing arithmetic and you want to figure out what's in this part of the curve. Can you use the TI program to do it? Of course you can! Walk me through. If I wanted to know what this area was right here. Walk me through. More probabilities. What kind of problem is it? It's I want area, so it's forward. Shade left. Or I guess left, what in this way? Left.
Negative.
Right bound of -1. There it is. Here it comes. It's going at 16%. That's because we rounded to different numbers before. No big deal. Mathematically, it's equivalent. Hey! Don't use your TIs. What area is 1 and above?
55.
That! It has to be that, right? Is curve symmetric? How about 1 all the way left forever? How about 1 all the way left forever? In other words, the percentage of IQs below 115.
1 minus 7. 8.
Busting out Project 1 skills. What up? She said 1 minus this number. That was wicked slick, Jolene. Yes. Yes. So we know this is 15.87%, right?
Yeah.
So if I want this, 100% minus that number gives me this, doesn't it?
84.5.
And or you could run normal left up to 1, which is exactly 1 minus that. So this is how forwards problems work. You have to have a standard normal curve. We'll deal with that on Thursday. But I want to look at one backwards problem, or maybe 2 backwards problems, because I want to make sure you understand what a backwards problem is too. And I want you to also understand why Veronica's question was a backwards problem. So let's start with Veronica's exact question. So run it again, more props. She asked a backwards problem. Her question was, where is Q2? Remember that question? It's an awesome question. Now I answered it very quickly, and I apologize for that, because I misunderstood what you thought. I thought you said Q1. So I said Q2, and I threw up really quickly, and then I realized, I'm like, duh, this would have been a great learning moment. But if you know Q2 is the 50th percentile, you know you're shading to the left of the curve, because percentiles always shade left, because you're interested in the data you're bigger than. So you're shading the ones you're bigger than. So we're going to shade to the left. How much to the left are we going to shade? 0.5 as a decimal, 50%. 0.5. When you press enter, it's going to show you the shade, and then down here on the left, it's going to show you the z-score that does that, which is exactly 0, which hopefully makes sense. 0 is in the middle of the curve, that's the 50 percentile, that's the median, that's the mode, that's all of them. Fair? Fair enough? But now a cooler question is, where's Q1? That was the next question. Where's the 25th percentile, right? And we did some arguing as to where we thought it was, and then eventually I relegated by telling you it's at -2/3, which you should have been like, to hell with you, rule, I don't believe you. Good, you don't have to believe me anymore. Now you can find it, right? So, more probabilities. Backwards, yes. Where is Q1? So where is the 25th percentile? That's a backwards problem. Let's shade to the left again. Let's shade to the left. What percent? 0.25. It's going to shade it for you. There he is. -0.67. That's your -2/3. Which means you know now where Q1 is, you know where Q2 is, and you know where Q3 is. That's not drawn very well. Q3 has to be the same distance away as Q1. 50% of your data is right between those two values, which means the other 50% is wildly variant by comparison, right? -2/3 to 2/3 is the middle 50%. Everything above 2/3 is the upper 25. That spreads out to infinity, friends, right? There's a lot of friggin' data out there. It's just that the most common data is right here. The most common data is right there. As you get outside that 50%, you start getting rarer and rarer and rarer. You start getting people that are 8.5 feet tall, or that are 3 foot 4 inches tall. You start getting very, very deviant data from the norm. From the norm. And if you want, you can make it a forwards problem. Let's go forwards between -0.67 and +0.67. It'll shade it for you, and then it'll tell you down there. I didn't draw it very well. Look at that. Ish. 50%. Rounding error. Rounding error because I don't have it displaying 2 decimals. And we'll see how to put this to work with Michael Phelps, Mark Spitz, human pregnancy, IQ scores on Thursday. So this is fun, except it doesn't help you answer any questions. It just is showing you how to fish. We'll do some fishing on Thursday. Ish fishing. We'll catch you guys in. Have fun with the quizzes. Hope you have as much fun doing it as I had making them. Yes.
We're still recording.
It is. Thank you. Shut that bad boy down.